Welcome to today's paper reading. Today's paper is titled, Classification Matters, Improving Video Action Detection with Class-Specific Attention. This paper was published on AR14 by Jinsung Lee and colleagues from Pohang University of Science and Technology and Naver Cloud. The abstract highlights that video action detection, VAD, faces more challenges in classification than in localization. The prevailing methods in VAD tend to prioritize actor regions but often neglect essential contextual information needed for accurate classification. To address this, the authors propose a model that reduces the bias towards actors and encourages attention to relevant context for each action class. This is achieved by assigning a class-dedicated query to each action class, allowing the model to dynamically focus on the most relevant areas for classification. The proposed model shows superior performance on 3 challenging benchmarks, using significantly fewer parameters and less computational resources. Video action detection, VAD, involves identifying actors and categorizing their activities in videos. This task has wide applications such as surveillance and sports analysis. VAD differs from object detection, OD, as it focuses solely on human actions, making localization simpler but classification more challenging. Classification in VAD requires fine-grained details in both appearance and motion. Empirical evidence shows that providing ground truth class labels improves VAD performance more than providing bounding boxes, highlighting the critical role of classification. Figure 1 illustrates the detection performance changes of the state-of-the-art methods, namely Tuber, EVAD, and ST-Mixer, on the AVA benchmark when ground truth boxes or class labels are provided. The figure clearly shows that providing ground truth class labels consistently yields more substantial improvement in detection performance compared to providing ground truth bounding boxes. This observation underscores the critical role of classification in enhancing video action detection performance, suggesting that the primary area for improvement lies in classification rather than localization. In video action detection, the focus is on generating actor-specific spatio-temporal tubes and predicting actions. Early studies combined spatial and temporal information for actor representation. More recent approaches use 2D person detectors and feature extraction for classification. Some studies capture spatio-temporal tubes instead of frame-by-frame detection, which our approach adopts for efficiency. In transformer-based architectures, DTR introduced a framework using cross-attention to capture object location and class. Adaptations like DBDTR enhance positional information for queries, which our method uses differently to guide class queries. For classification, methods explore actor-context relationships, often using transformer modules. However, these can suffer from biased attention towards actor regions, which we address in our approach. Figure 2 presents sample detection results and classification attention maps from 3 transformer-based models, Tuber, EVAD, and our proposed model. Each attention map highlights the regions where the model focuses to classify the action of the actor within the bounding box of the same color. Our model, unlike the others, generates an attention map for each class, which is indicated by the corresponding label beneath the map. This figure is best viewed in color to fully appreciate the differences in attention patterns and the specific regions each model focuses on for accurate action classification. The existing video action detection (VAD) models commonly use the transformer architecture, where an actor feature, represented by a query, gathers information from a video feature map, known as the context feature. These models generate an attention map to create classification features. However, this structure leads to a bias towards context features near the actor's location. Since the classification features are derived from a single attention map, all action classes share the same context feature information. This limits the model's observation scope to actor regions, potentially missing important regions that aid in classification. Additionally, the transformer weights are often trained to embed commonly shared semantics across different classes, leading to high attention values near actor regions and missing critical regions essential for classification. The proposed model architecture consists of a backbone network, a transformer encoder, and a transformer decoder. The model takes an input video clip X and outputs spatio-temporal tubes and per-frame action class predictions. A key component of the model is the classifying decoder layer, CDL, which uses learnable embeddings called class queries to encapsulate information specific to each class label. These class queries help the model to create more variation between features representing different action classes and mitigate bias towards common semantics. Additionally, the model includes a 3D deformable transformer encoder and a localizing decoder layer, LDL, to process and enrich the feature maps for classification. Figure 3 provides an overview of the proposed model's architecture, which consists mainly of a backbone, transformer encoder, and transformer decoder. The model takes an input video clip X and outputs predictions for each actor in the video. The key component of the model is the classifying decoder layer, CDL, which distinguishes itself by utilizing class queries, learnable embeddings designed to encapsulate information specific to each class label. These class queries help the model create more variation between features representing different action classes and mitigate bias towards common semantics. Additionally, the 3D deformable transformer encoder is modified to efficiently handle multi-scale feature maps, which are crucial for achieving more precise classification. Figure 4 illustrates the structure of the transformer decoder layers in our model, which are crucial for improved classification. The decoder is divided into two modules, the localizing decoder layer, LDL, and the classifying decoder layer, CDL. LDL specializes in gathering actor-related features from the encoded feature maps VENC and constructs localization features. On the other hand, CDL leverages the intermediate outputs of LDL, alongside class queries, to generate classification features. The figure uses symbol C and circle plus to indicate concatenation, multiplication, and summation operations, respectively. In the description of CDL, variables are indexed with the actor index I to simplify the process explanation. The cross-attention layers in CDL are designed to enhance the specificity of both actor and class, ensuring that the model focuses on the correct context for each action class. Figure 6 presents attention visualizations for the SIT class, highlighting the impact of attaching actor positional queries to class queries. In A, the model without this attachment shows class queries activating regions where a similar actor performs the same action, indicating an actor-agnostic activation issue. Conversely, B demonstrates the model with the attachment of actor positional queries, which mitigates this issue by improving actor specificity and preventing the activation of context belonging to wrong actors. The model's performance is evaluated on three datasets, AVA, JChimDB 51-21, and UCF 101-24. AVA is a large-scale dataset with 211,000 training frames and 57,000 validation frames, annotated sparsely at 1 fps. JChimDB 51-21 consists of 928 short video clips fully annotated with actions and bounding boxes. UCF 101-24 provides 3,207 untrimmed videos, requiring the model to distinguish between action and non-action frames. The evaluation criteria include mean average precision, MAP, at an IOU threshold of 0.5, applied at both frame level and video level. Ablation studies are conducted using CSN-152 and VITB backbones to assess the effectiveness of each model component. Figure 5 presents a comparison of detection results from a model utilizing a single-scale feature map on the left and multi-scale feature maps on the right. The detection threshold for both scenarios is set at 0.5, allowing for a direct visual assessment of the impact of feature map scale on detection accuracy and detail capture. This figure is crucial for understanding the benefits of employing multi-scale feature maps and enhancing the model's ability to detect fine details and overall performance. Figure 7 presents the classification attention maps generated by our model across various scenarios on AVA version 2.2. These maps illustrate the regions where the model focuses to classify the actions of actors, marked with the same color as their bounding boxes. The model dynamically adjusts its attention to crucial areas, such as near the actor's hands and arms for actions like hand shake or write. It also shifts attention to regions outside the actor's body, as seen in actions like listen to a person and watch, e.g. TV. Additionally, The model effectively differentiates class-relevant contexts in multi-actor scenarios, even when actors perform identical actions. Table 1 presents the results of ablation experiments conducted on each module of the model. The table compares the mean average precision, MAP, achieved with different configurations of the decoder and encoder modules. The baseline configuration includes a DTR decoder and a transformer encoder, achieving a MAP of 28.6. The introduction of the LDL, local dynamic layer, module with the transformer encoder increases the MAP to 29.1. Further enhancement is observed when the LDL module is combined with the CDL, class-specific dynamic layer, module, boosting the MAP to 31.4. The use of a 3D deformable transformer encoder instead of a standard transformer encoder, in combination with the LDL module, results in a MAP of 31.3. When the CDL module is added to this configuration, the MAP significantly improves to 33.5, demonstrating the effectiveness of the 3D deformable transformer and CDL modules in improving the model's performance. Table 2 presents ablation experiments, focusing on different methods to aggregate multiscale feature maps. The table highlights the performance metrics, MAP, for various configurations of the model. Key findings include the effectiveness of the 3D deformable transformer LDL plus CDL combination, which achieves the highest MAP of 33.5. Additionally, the transformer LDL plus CDL setup shows a significant improvement with a MAP of 31.4. The actor condition aggregation method is noted for its ability to provide actor-specific context, enhancing the model's performance on both datasets. Table 3 examines the effect of attaching actor positional queries to class queries in the classification process. The table compares the performance metrics with and without the attachment of actor positional queries. It highlights the actor-specific improvements in classification accuracy and the prevention of actor-agnostic activation, as supported by the results. The visualizations in Figure 6 further illustrate the differences in activation regions with and without the actor positional queries, reinforcing the benefits of their attachment. Table 4 presents ablation experiments on various methods to combine actor and context features in video action detection, VAD. The methods explored include summation, concatenation followed by 1D convolution, and cross-attention. The results indicate that simple summation of features achieves the highest performance on both AVA and UCF datasets, with scores of 33.5 and 85.9 respectively. Concatenation with 1D convolution yields slightly lower performance at 31.8 and 84.7 for AVA and UCF, while cross-attention results are 31.3 and 81.3, showing the least effective combination method among the tested approaches. Table 5 presents a comprehensive performance comparison of various models across three benchmarks, K600, K700, and K400. The table highlights the MAP, mean average precision, scores for each model, indicating their effectiveness in action detection tasks. The D column specifies whether the model employs an off-the-shelf detector, which can significantly influence performance. Notably, our model outperforms several state-of-the-art models, including STMixer and EVAD, across different backbones and datasets, demonstrating its robust and competitive performance in video action detection. Table 6 presents an efficiency comparison of various models on the JHMBB and UCF datasets. The table highlights the computational resources, including parameters, flops, and inference time, required by different models to generate a single tube. Notably, our model, utilizing ViTB as the backbone, demonstrates competitive performance with significantly fewer parameters, 117.8 m, and lower flops, 3.26 t, compared to other models like EVAD, 185.4 m parameters and 10.68 t flops. Additionally, our model achieves the fastest inference time at 432.0 milliseconds, contrasting with EVAD's 8,363.1 milliseconds. This efficiency is crucial for real-time applications and large-scale processing, underscoring the model's advancements in computational efficiency. Table 7 presents a performance comparison among the latest video action detection (VAD) models, including tuber, STMixer, EVAD, and our model. The table highlights key metrics such as the number of parameters, params, floating point operations per second, flops, inference time, INF time, and mean average precision, MAP, for both frame level, FMAP, and video level, VMAP, on datasets JHMDB and UCF. Our model demonstrates competitive results with fewer parameters and the least flops, indicating its efficiency in processing video data for action detection tasks. The model introduced by the authors has achieved state-of-the-art performance on challenging benchmarks and is the most efficient network for inference. However, there are limitations to the current model. The decoder architecture does not exchange information across frames, which places a significant burden on the encoder to capture temporal dynamics. Future studies could focus on sparsely collecting class information from the spatial domain and using residual memory to capture temporal dynamics, aiming to improve performance. Thank you for watching.